In mathematics, factorization or factoring is the decomposition of an object into a product of other objects, or factors, which when multiplied together give the original. For example, the number 15 factors into primes as 3, 5, and the polynomial x2 of 4 factors as x plus 2. In all cases, a product of simpler objects is obtained. The aim of factoring is usually to reduce something to a basic building blocks such as numbers to prime numbers, or polynomials to irreducible polynomials. Factoring integers is covered by the fundamental theorem of arithmetic and factoring polynomials by the fundamental theorem of algebra. Viète's formulas relate the coefficients of a polynomial to its roots. The opposite of polynomial factorization is expansion, the multiplying together of polynomial factors to an a-OE expanded polynomial, written as just a sum of terms. Integer factorization for large integers appears to be a difficult problem. There is no known method to carry it out quickly. Its complexity is the basis of the assumed security of some public key cryptography algorithms, such as RSA. A matrix can also be factorized into a product of matrices of special types, for an application in which that form is convenient. One major example of this use is an orthogonal or unitary matrix, and a triangular matrix. There are different types: Q or decomposition, LQ, QL, RQ, RZ. Another example is the factorization of a function as the composition of other functions having certain properties. For example, every function can be viewed as the composition of a surjective function with an injective function. This situation is generalized by factorization systems. Integers. By the fundamental theorem of arithmetic, every positive integer greater than 1 has a unique prime factorization. Given an algorithm for integer factorization, one can factor any integer down to its constituent primes by repeated application of this algorithm. For very large numbers, no efficient classical algorithm is known. Polynomials. Modern techniques for factoring polynomials are fast and efficient, but use sophisticated mathematical ideas. These techniques are used in the construction of computer routines for carrying out polynomial factorization in computer algebra systems. The more classical hand techniques rely on either the polynomial to be factored having low degree or the recognition of the polynomial as belonging to a certain class of known examples and are not very suitable for computer implementation. This article is concerned with these classical techniques. While the general notion of factoring just means writing an expression as a product of simpler expressions, the vague term simpler will be defined more precisely for special classes of expressions. When factoring polynomials, this means that the factors are to be polynomials of smaller degree. Thus, while is a factorization of the expression, it is not a polynomial factorization since the factors are not polynomials. Also, the factoring of a constant term, as in, would not be considered a polynomial factorization since one of the factors does not have a smaller degree than the original expression. Another issue concerns the coefficients of the factors. In basic treatments, it is desirable to have the coefficients of the factors be of the same type as the coefficients of the original polynomial, that is, factoring polynomials with integer coefficients into factors with integer coefficients, or factoring polynomials with real coefficients into polynomials with real coefficients. It is not always possible to do this, and a polynomial that can not be factored in this way is said to be irreducible over this type of coefficient. Thus, x2-2 is irreducible over the integers and x2 plus 4 is irreducible over the reals. In the first example, the integers 1 and -2 can also be thought of as real numbers, and if they are, then shows that this polynomial factors over the reals. Similarly, since the integers 1 and 4 can be thought of as real and hence complex numbers, x2 plus 4 splits over the complex numbers, that is. The fundamental theorem of algebra can be stated as, every polynomial of degree n with complex number coefficients splits completely into n linear factors. Since complex roots of polynomials with real coefficients come in conjugate pairs, This result implies that every polynomial with real coefficients splits into linear and irreducible quadratic factors with real coefficients. Even though the structure of the factorization is known in these cases, finding the actual factors can be computationally challenging. General methods. There are only a few general methods that can be applied to any polynomial in either one variable or several variables. Highest common factor. Finding, by inspection, the monomial that is the highest common factor of all the terms of the polynomial and factoring it out as a common factor is an application of the distributive law. This is the most commonly used factoring technique. For example, factoring by grouping, a method that is sometimes useful, but not guaranteed to work, is factoring by grouping. Factoring by grouping is done by placing the terms in the polynomial into two or more groups, where each group can be factored by a known method. The results of these partial factorizations can sometimes be combined to give a factorization of the original expression. For example, to factor the polynomial, group similar terms, factor out the highest common factor in each grouping, again factor out the binomial common factor. While grouping may not lead to a factorization in general, if the polynomial expression to be factored consists of four terms and is the result of multiplying two binomial expressions, then the grouping technique can lead to a factorization, as in the above example. Using the factor theorem. For a univariate polynomial, p, x, the factor theorem states that a is a root of the polynomial equals 0, also called a zero of the polynomial, if and only if is a factor of p, x. The other factor in such a factorization of p, x, can be obtained by polynomial long division or synthetic division. For example, consider the polynomial by inspection. We see that 1 is a root of this polynomial, so is a factor of the polynomial. By long division we have, univariate case, using properties of the roots. Quadratic polynomials can sometimes be factored into two binomials with simple integer coefficients by use of Viète's formulas, without the need to use the quadratic formula. In a quadratic equation, this will expose its two roots. The formula would be factored into where and each binomial can then be set equal to 0, and solving for x reveals the two roots. Consider for example 2x2 of 5x plus 2 equals 0. Because a equals 2 and mn equals a, mn equals 2, which means that of m and n, one is 1 and the other is 2. Now we have, za plus aq, equals 0. Because c equals 2 and pq equals c, pq equals 2, which means that of p and q, one is 1 and the other is 2 or one is a 1 and the other is a 2. A guess and check of substituting the 1 and 2, and a 1 and a 2, into P and Q tells us that 2x2a5 za plus a2 equals a0 factors into za a2, and equals a0, giving us the root za equals a 0.5, a2. Note, a quick way to check whether the second term in the binomial should be positive or negative is to check the second operation in the trinomial. If it is the plus, then check the first operation. If it is the plus, the terms will be positive, while if it is a, the terms will be negative. If the second operation is a, there will be one positive and one negative term. Guess and check is the only way to determine which one is positive and which is negative. If a polynomial with integer coefficients has a discriminant that is a perfect square, that polynomial is factorable over the integers. For example, consider the polynomial 2x2a plus a2 za a12. If the values of the expression are substituted into the quadratic formula, the discriminant b2aa4ac becomes 22aaa, 4aa, a2aa, a12, which equals 100. 100 is a perfect square, so the polynomial 2x2a plus a2 za a12 is factorable over the integers. Its factors are 2 and. Now consider the polynomial x2a plus a93 za a2. Its discriminant, 932aa4aa, a1aa, a2, is equal to 8657, which is not a perfect square. So x2a plus a93 za a2 cannot be factored over the integers. Finding rational roots. If a polynomial, f, x, has a rational root, pq, then by the factor theorem f, x, has the factor. If, in addition, the polynomial f, x, has integer coefficients, then q must evenly divide the integer portion of the highest common factor of the terms of the polynomial, and, in the factorization of f, x, only the factor will be visible. If a polynomial with integer coefficients, say, has a rational root pq, where p and q are integers that are relatively prime, then p is an integer divisor of n and q is an integer divisor of ao. If we wish to factorize the polynomial, we could look for rational roots pq where p divides -6, q divides 2 and p and q have no common factor greater than 1. By inspection we see that this polynomial can have no negative roots. Assume that q equals 2, substitute x equals p/2 and set the polynomial equal to 0. By dividing by 4, we obtain the polynomial equation that will have an integer solution of 1 or 3 if the original polynomial had a rational root of the type we seek. Since 3 is a solution of this equation, the original polynomial had the rational root 3/2 and the corresponding factor. By polynomial long division we have the factorization. For a quadratic polynomial with integer coefficients having rational roots, the above considerations led to a factorization technique known as the Act Method of Factorization. Suppose that the quadratic polynomial with integer coefficients is, and it has rational roots, p, q and uv. Both q and v must be divisors of a, so we may write these fractions with a common denominator of a, that is, they may be written as ra and s then. So, we have where rs equals ac and r plus s equals b. The Act method for factoring the quadratic polynomial is to find r and s, the two factors of the number ac whose sum is b, and then use them in the factorization formula of the original quadratic above. As an example, consider the quadratic polynomial. Inspection of the factors of ac equals 36 leads to 4 plus 9 equals 13 equals b. Recognizable patterns. Difference of two squares. A common type of algebraic factoring is called the difference of two squares. It is the application of the formula to any two terms, whether or not they are perfect squares. This basic form is often used with more complicated expressions that may not at first look like the difference of two squares. For example, some difference of two cubes. Another formula for factoring is the sum or difference of two cubes. The sum can be factored by, and the difference by, difference of 2/4 powers. Another formula is the difference of 2/4 powers, which is some difference of 2 nth powers. The above factorizations of differences or sums of powers can be extended to any positive integer power n. For any n, a general factorization is. The corresponding formula for the sum of 2 nth powers depends on whether n is even or odd. If n is odd, b can be replaced by ab in the above formula, to give. If n is even, we consider two cases. 1. If n is a power of 2, then is unfactorable. 2. Otherwise, where m is odd. In this case we have. Specifically, for some small values of n we have binomial expansions. The binomial theorem supplies patterns of coefficients that permit easily recognized factorizations when the polynomial is a power of a binomial expression. For example, the perfect square trinomials are the quadratic polynomials that can be factored as follows. And some cubic polynomials are four-term perfect cubes that can be factored as. And in general, the coefficients of the expanded polynomial are given by the nth row of Pascal's triangle. The coefficients of have the same absolute value but alternate in sign. Other factorization formulae. Using formulas, any quadratic polynomial can be factored using the quadratic formula, as follows. Where and are the two roots of the polynomial, found with the quadratic formula. The quadratic formula is valid for all polynomials with coefficients in any field except those that have characteristic 2. There are also formulas for cubic and quartic polynomials which can be used in the same way. However, There are no formulas in terms of the coefficients that exist for higher-degree polynomials by the Abel-Ruffney theorem. Factoring over the complex numbers, sum of two squares, if a and b represent real numbers, then the sum of their squares can be written as the product of complex numbers. This produces the factorization formula. For example, can be factored into some difference of two nth powers over the field of the algebraic numbers. A thorough factorization can be obtained over the field of the algebraic numbers, as showed by the following reduction formulae, which are proved going through the complex conjugate roots of the sum of two even powers is factored by the difference of two even powers is factored by the sum or difference of two odd powers is factored by. For instance, the sum or difference of two fifth powers is factored by, and the sum of two fourth powers is factored by. Matrices. Unique factorization domains. Euclidean domains. See also, completing the square, monoid factorization, Pascal's triangle, prime factor, Fermat's factorization method, Euler's factorization method, integer factorization, multiplicative partition, partition, a way of writing a number as a sum of positive integers. Program synthesis, table of Gaussian integer factorizations, notes. References, Dixon, Leonard Eugene, First Course in the Theory of Equations, New York, John Wiley and Sonser, Veit, William Benjamin, College Algebra, Boston, D.C. Heath and Company. Klein, Felix, Elementary Mathematics from an Advanced Standpoint. Arithmetic, Algebra, Analysis, Dover, External Links, Haswinkel, Michiel, ed., Factorization of Polynomials, Encyclopedia of Mathematics, Springer, ISBN A978-1-55608-010-4, 100 million numbers factored on HTML pages. WIMS Factoris is an online factorization tool. Wolfram Alpha can factorize 2.